Hey, welcome back to Geometry. This is section 7.2, Similar Polygons. The objective in this lesson is to identify and apply similar polygons. It's essential that you understand you can use ratios and proportions to decide whether two polygons are similar and to find unknown side lengths of similar figures. So you'll remember back to the exploration that we did in class with the shadows. Your shadow and your original figure, they came out proportional because they were similar. Similar figures have the same shape but are not necessarily the same size. Like the shadow, one was small, one was large. The symbol for similar is this symbol. It's just the tilde that's on top of congruence. You know how congruence was the equal sign with the squiggly above it? Similar is just the squiggly. It's not equal. So it's not equal at all. It's just the squiggly at the top, similar. So key concept here, similar polygons. Two polygons are similar polygons if corresponding angle, you'll remember corresponding means the matching, if the corresponding angles are congruent and if the lengths of the corresponding sides are proportional. So they're different than congruent figures in that their sides are not the same length. The sides are proportional, but the angles are equal. So they have corresponding congruent angles and proportional sides. So in this diagram, we have this quadrilateral ABCD, and it's written ABCD is similar to, that's what this means, GHIJ. You'll notice it's all color-coded for you. You could use colored pencils on your notes. So angle A is congruent to angle G. Angle B is congruent to angle H. Angle C is congruent to angle I. And angle D is congruent to angle J. They have the matching rainbow arcs. This is the important part, the ratio of their sides. We learned yesterday about extended ratios. There are 4 sides, so we're going to have 4 ratios. So it's going to be a really long proportion. So notice AB is over GH. They're corresponding sides, just like we did with congruent figures. A matches to G and B matches to H. So AG is A is over G and B is over H. You'll notice that in every proportion. So AB, that's this side here, is proportional to GH. There's one rule of thumb you have to follow when you're writing these ratios. Notice AB is the smaller figure. You'll notice that throughout this entire proportion that we're writing, the small figure is on top and the larger figure is on the bottom. You have to decide which one you're going to put on top and which one you're going to put on the bottom, and then you have to stick with that. So AB over GH, BC, that's this side, over HI, CD over IJ, and then AD over GJ. So you'll notice that the letters match, just like when we were doing congruent figures. In this case, they're not equal, they're proportional. Whenever you cross multiply, every proportion will work. Every single one. When you cross multiply, they should come out so that they are equal. If the figures are similar, they should come out equal. You write a similarity statement with corresponding vertices in order, just like a congruent statement. So remember back when we were saying like triangle ABC is congruent to triangle DEF? Well, it's the same, but you don't put congruent in there. You put the symbol for similar. When 3 or more ratios are equal, you can write an extended proportion. We learned about those on last night's notes. A scale factor, this is an important word for you to note. Scale factor is the ratio of the corresponding linear measurements of two similar figures. All the sides, all the ratios of the sides will reduce to the same thing. So in this example, these two triangles are similar. triangle ABC is similar to triangle XYZ. BC over YZ is 20 over 8. It reduces to 5 to 2. The thing is that no matter what pair of corresponding sides you pick, like AB over XY, right? Because AB are the first two letters and XY are the first two letters. 15 over 6. These can both be reduced by 3. 3 goes into 15 5 times. 3 goes into 6 twice. 5 to 2. Let's take a look at AC and XZ. They are corresponding sides. AC to XZ, it's 25 over 10. These can both be reduced by 5. 5 goes into 25 5 times. 5 goes into 10 twice. So the scale factor of triangle ABC to triangle XYZ is 5 to 2. Or you can write it like this, 5 to 2. So the ratio of all the corresponding sides reduce to the same ratio. So let's understand similarity. If triangle MNP is similar to triangle SRT, what are the pairs of corresponding congruent angles? So this is just like when we did congruent shapes. The pairs of corresponding angles are all congruent. And you don't really even have to look at the picture. Remember when we did congruent shapes? We really just looked at the letters. M comes first, S comes first. So angle M is congruent to angle S. Then we have N and R. Angle N is congruent to angle R. And then we have P and T. Angle P is congruent to angle T. Here's where the different part comes in. The sides are not congruent. The sides are proportional. So what is the extended proportion for the ratio of the corresponding sides? Well, we had M matching to S. Now, this is where you have to decide which triangle is going to go on top. I'm going to put this first triangle on top. This first triangle on top and the second one on the bottom. So I have M, which was my first letter, and then I have N, which was my second. So it's this side right here, MN, and it corresponds to what side? It goes to SR. So it goes to SR. MN corresponds to SR. Then, in my proportion, all my ratios are going to be equal. If these two triangles are similar, then that means that all of the corresponding angles are congruent and all of the corresponding sides are proportional. That's the definition of similar. So, we have our next sides, NP, and that is corresponding to RT. So it's RT. And then what's the last one? We have 3 sides, so we're going to have 3 ratios. The last one, it's going to be MP. And what does it correspond to? I have segment MP, and it corresponds to, what's the matching side in the larger triangle? ST. So this is an extended proportion for the ratio of the corresponding sides. So let's determine similarity. Are the polygons similar? First thing you want to do is look at the angles. Well, angle M has 1 arc, and it's congruent to angle W. Angle J has 2 arcs, and it's congruent to angle T. Angle K is a right angle, and it's congruent to angle U. And then angle L and angle V are congruent. So all of the angles are congruent. So angle M is congruent to angle W. Angle J is congruent to angle T. Angle K is congruent to angle U. Notice how I'm being very organized here. I'm putting all of this first shape. This is 1, this is 2. Angle L is congruent to angle V. So all of the sides now have to be proportional in order for me to determine if these two shapes are similar. So we want to determine, just because the angles are congruent doesn't mean that they are similar. So I'm going to write my extended ratio of my sides. So I have MJ over WT. See where I'm getting that from? MJ WT. Is it equal to JK over TU? So let's see if this first one works. We could write a proportion for all 4 sides right now, but let's see if the first one works. If one of them doesn't work, then these are not similar. So MJ, that's here, it's got 6, and WT is 6. So 6 over 6. Is it equal to 12 over 6? Well, you know right off the bat, 6 over 6 reduces to 1. 12 over 6 reduces to 2. Are those equivalent fractions? They are not equivalent fractions. So you know right away that they are not congruent. They are not similar figures. But if you cross multiply, you're going to get 36. And 6 times 12 is 72. They are not equal. So because just even one pair is not proportional, these are not similar. They're not similar. All pairs of corresponding sides have to be proportional in order for them to be similar. So these two, they're not similar. All of their corresponding angles are congruent, but their sides are not proportional. So let's take a look at this triangle. Are these similar? If they are, write a similarity statement and give the scale factor. So we're going to do the same thing. Let's take a look at this. Angle C is congruent to angle F. Angle A is congruent to angle D. And angle B is congruent to angle E. And again, notice I used the same triangle each time when I started. I went 1 arc, 2 arc, 3 arcs just to stay organized. So I want to say, is CA over FD, right? CA over FD, is that equal to AB over DE? And is that equal to CB over FE? So let's plug in the numbers and see if it works. CA is 8, FD is 10. 8 and 10. Is it equal to 12, which is AB, over DE, which is 15? Now notice the picture's misleading. These triangles, they're turned. They're not facing the same direction. And then CB, which is 16 over 20. It's important to be organized here. A couple ways you can do this. You can cross multiply to see if you have equivalent fractions, or you could reduce them all to see if they reduce to the same thing. Either way, you're going to get the same answer. So when you cross multiply every pair, you're going to get 120 equals 120. So this one works. When I cross multiply the next pair, 12 times 20 is 240. And 16 times 15 is 240. So that one works. And then finally, this last pair here, 8 times 20 and 10 times 16, 160 equals 160. So no matter what combination I try, when I use the cross product property, they all work. Another way that you could have done this would be to reduce all of these. Do they all reduce to the same thing? If they do, then you know that they are similar. So 8 over 10 reduces to 4/5. 12 over 15, well, 3 goes into 12 4 times, 3 goes into 15 5 times. 4 goes into 16 4 times, 4 goes into 20 5 times. So these all reduce to the same ratio, 4/5. Our scale factor would be 4/5. 4 to 5. We have a 4 to 5 ratio here, or 4/5. And the way that you write a similarity statement would be to say that triangle CAB, I'm just getting these letters from right here, CAB is similar, not congruent, no equal sign, to triangle FDE. So this is your similarity statement. And our scale factor, this is our scale factor. So that's what's meant by those. Similarity statement and scale factor. All right, we can use similar polygons. If you know two polygons are similar, then you know that the ratios of their sides are proportional. If we want to find the value of x when we know that ABC is similar to EFGD, well, here's x. FG, it corresponds to this side, BC. FG corresponds to BC. How many ratios do you need in order to solve? Well, you just need 2, so you can cross multiply, use a cross product property. So I have the small one on top. FG is the small one, so I need to pick another side of the small one. I do have this one, EF, but I don't know what Y is, and I can't solve for X and Y in the same equation. So I'm actually going to use this one, ED. Over, ED corresponds to AD in the large shape. So now I'm going to plug in those values. FG is X over 7.5, which was BC. Is it equal to? It is equal to. ED is 6 over AD, which is 9. So I want to use the cross product property here to solve for the value of x. I'm going to say 7.5 times 6 and 9 times x. 9 times x is 9x, and 7.5 times 6 is 45. And when I divide by 9, x is going to equal 5. And now because I know that, I could find y. But we'll move on from here to the next example. We'll practice more of these tomorrow. So similarity, a real-life application of that is a scale drawing. The scale is the ratio that compares each length of a model to an actual. You might remember we did a little of this last year in algebra. Units in a scale factor can be different as long as you put them in the same place. If you're putting model over actual, then in your other ratio, you have to put model over actual. So you can have inches over feet in this situation. So you want to make a scale drawing of New York's Empire State Building using a scale of 1 inch to 250 feet. So this is model over actual. So the ratio we're going to write is going to be model over actual. We're going to stay consistent with that. If the building is actually 1,250 feet tall, how tall should you make the building in your scale drawing, in your model? So that's the model and that's the actual. We don't know. How tall? How? I don't know. So my model is this. 1 inch over 250 feet is equal to model over actual. Do you know how tall the model has to be? You don't. So it's x inches over the actual is 1,250 feet. So notice in the ratios we have model over actual equals model over actual. Again, using that cross product property, we can solve. So we're going to have 250x is equal to 1 times 1250 is 1250. Then you want to divide by 250. So x is going to equal 5, and what's on top? inches. When you plug it in and cross multiply, you should get the same product. So if you were drawing a model of the Empire State Building and you were using a scale of 1 inch is 250 feet, then your model would be 5 inches tall. We'll practice this more tomorrow. Be ready for the notes quiz.